This is Jake White, and this is my Physics Lab 2 video. So in this lab, we'll be investigating charge tape, and this is part 2 of the experiment that we're going to continue from Lab 1. And here's the intro and results. So in this lab, I continued the work done in Lab 1 with charge tape. However, I created a more sophisticated model to represent the tape instead of using point charges to represent the tapes. This experiment is designed to investigate the interactions of charged objects in order to effectively model the physical interactions. And then at the bottom you can see the presentation structure if you're interested. So here's the results from Lab 2. So you can we got the total electrical force, and we got the electrical force was equal to the gravitational force and the net charge of one tape. And here is our Lab 1 overview. So here's the procedure. I created 2 charged pieces of tape by sticking them to a base tape and pulling them apart. I then rubbed a pin in my hair, creating a negatively charged pin, and held it near the charged tape. The pin and tape were attracted to each other, meaning that the charged pieces of tape were positively charged. I suspended one charged tape using 2 textbooks as support, and then held another charged tape below and recorded the change in position of the suspended charged tape. I then used GlowScript to create a computational model of step 3, which I used to calculate the charges of the tape. So here's the measurements from Lab 1, and here's the results. You can see it's just simple point charges that I use to model each tape. The green arrows are the electrical force, and the yellow arrows the gravitational force. So here's an overview of Lab 2. So here's the fundamental physics involved. First Coulomb's law, and then Newton's second and third law, which I use with the gravitational force. And finally superposition, which is used to divide up the tape into smaller segments and then summing up the charge of each segment. So assumptions. For this lab, I made several assumptions. Air resistance is ignored. Each segment of tape can be considered a point charge, and all segments are equal in charge, and when summed up, they're equal to the total charge of the tape. So here's Lab 2 coding. So on the left, you can see basic constants, and then at the bottom, you can see where I define the E field. Essentially using the equation from Lab 1, I just kind of put that into the definition of E field. And then on the right, you can see where the line charge is defined, which creates point charges along a line for the bottom and top tape. So here's the coding continued. So at the top, you can see where the electrical force and the gravitational force are defined. And then right below that, you can see where the electric field vectors for each point charge is created. And then we just have the arrows, and then finally the print statements at the bottom. So here's the computational model that we get from this lab. We get that the magnitude of the electrical force is 1.96 times 10 to the negative third, which is equal to the gravitational force, so that checks out. The green arrows are the electric field vectors from each point charge, and the white arrow is the electric force, while the yellow arrow is the gravitational force. Okay, so conclusion. What if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So the calculated value of charge was 1.66 times 10 to the negative 8th using the point charge method, and 2.47 times 10 to the negative 8th using the line charge method. This is a 49% difference in calculated values for charge, so quite a bit of difference. And so why do these estimates differ? Which value is more likely to be closer to the real value, and why? These estimates differ as 2 different methods were used to model the tape. The value from the line charge method is likely more closer to the real value, as the line charge more accurately approaches the actual physical interaction. In fact, as the number of point charges in the model increases, the value for the charge approaches the actual value. And that's all I got.